Okay, good morning, everyone. I suppose we have to talk in English. No, in this event. Okay, I'll try my best. Good morning, everyone. We are here for the doctoral meeting for a short presentation of Pablo of his proposal of PhD. That the title is Enhancing Few-Shot Object Detection through Pseudo-Label Mining, and it's directed by Manuel and Danny Collins. So I don't know if you can start, more or less 20 minutes. Let's do this flexible. So I think that if there are questions in any moment, if you don't mind, I think that anyone can raise their hand and ask him. Okay, great.
So thank you, Thomas. I'm going to start introducing what is object detection, which involves determining the class and position of objects in images. So here we have an example. We have a dog and a cat, and our goal is to frame each of the animals with bounding boxes and determine which is which. Currently, this task is usually solved using deep learning techniques, namely detectors based on convolutional neural networks like can be faster CNN, or more recently based on transformers like BTET or IMTIT. Regardless the type of detector used, they all have one common feature. They need to be trained on large databases of human audited labels. The problem is that this data is usually costly to obtain and also limit the final performance of the detectors. So here the question is, can we achieve good detection performance with minimal label data? To answer this question, few-shot emerges. In few-shot, what we try to do is extract general knowledge from large collections of base data and adapt quickly to the novel and seen data. A few-shot object detection tries to incorporate these few-shot techniques into the detection problem, and it's usually solved following these two techniques, fine-tuning and meta-learning. A fine-tuning approach the problem as a transfer learning situation with two training stages. A first training stage on abundant base data, and a second fine-tuning on the unseen novel data. In contrast, meta-learning approaches what try to do is obtain a good distance metric that can be used to compare support sets with query images. The problem is that none of these approaches exploit the abundant unlabeled information that can be in many real-time situations. So here we ask ourselves, can we expand the original training set by mining pseudo-labels in unlabeled data? Of course we can, and to this end we propose our method expand. So we start from a data set divided in three annotation sets: the base, the novel, and the unlabeled. The base has many objects of base categories. The novel has only k-shot objects of novel categories where k is typically a value below 30 to be in a few-shot setting. And the unlabeled consists of images with unlabeled objects. So in our method, first we train a detector on the labeled data. Then we use this detector to mine pseudo-labels in the unlabeled images. The problem is that these pseudo-labels usually have wrong categories or are badly framed. So here is where we propose our method expand, which is a method that filters out many of these bad quality detections. At the end, the obtained pseudo-labels together with the original label data can be used to train and improve any detector. It's worth mentioning that our method can be integrated with any few-shot detector to improve them. So here we have an overview of expand steps, namely initial filtering, class confirmation, boss confirmation, and sampling. The initial filtering just applies a soft confidence threshold to remove very low quality detections. The class confirmation tries to remove misclassified detections, that means detections with incorrect category. The boss confirmation tries to remove bad friendly boxes, and the sampling just performs a class rebalance to a maximum imbalance factor. So now let's delve into the class confirmation and box confirmation modules, which are the more important ones. So the class confirmation, we built it as a fused classifier on the meta-learning approach. So it tries to learn a good distance metric that can be used to compare queries to set images. So here we have an example. We have a person labeled as a person, a cat labeled as a cat, and a dog labeled as a dog. The class confirmation in inference compares each of these pseudo-labels to the expected support sets in order to remove or keep them based on its similarity. This is the model of the class confirmation. We follow a contrastive learning setting, so we have 3 branches. The upper branch receives the image expected to belong to the query class. The middle branch receives the images expected to not to belong to the query class, but are the support set. And the last branch receives the support set expected to not belong to the query class, but only in training. So first, a feature extractor processes the 3 elements to obtain the feature maps. Here we leverage the recent advancements in self-supervised learning, and we adopt as our backbone a tiny pre-trained bit. Also, since the positive and negative branches, these two, receive multiple images, the final feature map is obtained by averaging the individual feature maps. After the feature extraction, the feature maps, these 3, are reduced to vectors EQ, EPOS, and INEG. EQ is concatenated with EPOS to obtain the positive embedding, but also with INEG to obtain the negative embedding. The final fully connected layers just perform the binary classification using as input the concatenated vectors. The training of the class confirmation module follows a 2-stage fine-tuning, so first on base abundant classes, and then in the novel and sim data. To optimize this model, we adopt a multitask loss function, which has 2 parts. A classification part, LCE, which is just a cross entropy, but also a discrimination part, L3, which is a triplet loss. We include this triplet loss to force the model to generate highly discriminative embeddings, and in this way improve the final classification. Okay, and on another hand, the box confirmation module, we built it as an intersection over union estimator. So it tries to predict the expected IOU between a real box and the pseudo-label box. So here we also have an example. We have different objects, and in inference, the box confirmation, what tries to do is predict a confidence regression score that can be used to remove the bad frame ones. So this is the model of the box confirmation. It receives as input a pseudo-label and the full image that contains it. Similar to the class confirmation, here we also use a feature extractor to process the full image and obtain the feature maps. And we also harness the benefits of self-supervised learning. So we adopt as our backbone a my pre-trained bit. Then the specific features of the object, in this case the person, are obtained through the row-align method between the multi-scale feature maps and the full image. And then are fed into a regression header, which consists of 4 convolutional layers and 2 fully connected layers. The final fully connected layer just has a single output value with sigmoid activation to produce a value between 0 and 1 that can be interpreted as an estimation of IOU. Similar to the class confirmation, the box confirmation module training of the box confirmation module also follows a 2-stage fine-tuning, first on base data and then in novel data. But one important difference is that here the novel data is synthetically generated, as we can see in this image, by applying random offsets in the four main primary directions. So with this, we finish the methodology part, and we can go through the results we obtain with expand. So to validate expand, we use two datasets, COCO and BOC. COCO has 60 base categories and 20 novel categories and more than 100,000 images. And BOC has 20 rotating categories with more than 11,000 images. For fair comparisons with state-of-the-art works, we use the two main evaluation protocols, TFA and FSRW. TFA used 10 different supersets, and FSRW used a single superset with 10 different repetitions. Also, to prove that expand is agnostic to any detector and can be integrated with anyone, we integrated with 5 different detectors, some of them based on convolutional neural networks and others based on transformers. So this table shows the ablation studies. The rows represent different expand steps, and the columns the 5 different detectors. So we can see in the first row how training with all the pseudo-labels before expand causes a drop of 5 points. But training with expand at different stages increases the AP interactively. Also, we can see in the third and fourth rows how the class confirmation, row 3, and boss confirmation, row 4, increase the AP in a complementary manner. In the right figure, we have the distribution of pseudo-labels before and after applied expand. So here we can see how the number of pseudo-labels after expand decreases, but which is more important, the proportion of the pseudo-label increases. These are the final results on COCO dataset. So the left table shows different state-of-the-art feature detectors, and the right table shows the integration of expand with 5 of them. So from this data, we can highlight 3 things. First, expand is valid because improves all base detectors within margins between 1 and 5 points. Also, we can see how the transformers-based methods bit-dit and im-dit benefit the most from expand up to 6 points. And also, we can see how im-det with expand sets a new state-of-the-art in this dataset. These are the final results in BOC dataset. Similar to COCO, here expand also improves all base detectors. In this case, and in contrast to COCO, the transformer-based methods do not outstand. This highlights the data-hungry nature of transformers. And here we also set a new state-of-the-art with the combination of expand and D and R. So just to summarize this work, in this work we present expand, a mining pipeline that generates high-quality diverse pseudo-labels. Expand is grounded on class and box confirmation models, which removes misclassified or bad-friendly pseudo-labels. And with expand, we set new state-of-the-art on both COCO and BOC datasets. Thank you very much. That's all.
Thank you, Pablo. Questions?
Hey, Pablo. Thank you for your talk. So, can you talk a bit about your future and about the future work? I mean, is it going to be about improving this method or?
No, in fact, now I'm working in another similar related topic, which also exploit and label information, but in a different manner. So here, I use the label and the class confirmation model. Now I'm working in a semi-supervised setting, which tries to iteratively improve this data instead of mining altogether. I don't know if I explained to you.
You explained it probably very well.
So, yeah, about the question, in what phase of your PhD? Are in the middle and the finishing?
No, I'm in the middle start. Yeah.
More questions? I would like to ask about detail because I'm from the computer architecture area, so I didn't catch most of the presentation. I only catch the general ideas. So I'm going to ask about the implementation. What libraries are you using?
Mainly I use in PyTorch, but with a framework which is called Doctoral, but it's PyTorch.
It's Python.
Yeah.
So you select it because it's the state of the art? Or?
Yes, and when we iterate expand with different methods, their methods are already implemented, so we have to adapt to them. So most of them are implemented in PyTorch. So
Okay. And the one then in the here in the cluster in the
yes, in this cluster or sometimes in the Thesga, but
in the
yes,
Cerca. Okay, because Cerca now have
GPUs. Yeah.
several GPUs. And other question, but maybe this is for your advisor, is all these methods are applied to image or video, but it's possible to move this to 3D image. I'm thinking in non-image point clouds. There are several people here in Institute, that work with 3D point clouds that are different, are other kind of data, completely different of image. So I don't know if there are, and I know that there are people that are applying techniques of machine learning to classify 3D point clouds, but are quite basic.
I don't know much about 3D clouds, but probably, in fact, in CVPR, there are some papers doing that, mostly on object detection, but they are not specifically working with a limited number of level data. So maybe this could be adapted to 3D point clouds.
I asking this because one of the problem of 3D point clouds, there are no level data. It's very difficult if you got an image from taken from an helicopter.
Well,
Manually classify the data is very, very difficult, and there are no ground truth. There are very few that are ground truth.
my experience in 3D data is when I work in robotics doing SLAM. But typically this data, I mean, the features of the objects are quite different from the features you have from a conventional image.
Yeah.
So I'm not totally sure if this kind of architecture would work in that field, but the general idea could work.
It's a point to study. So change the
scope.
the objective, the scope.
It's in the second year, so I think it's
to be the point cloud.
maybe for the postdoc.
Okay, more questions? Please. No. So, again, Pablo, nice presentation.